discussed how we're able to figure out the volume of a sphere, right? So what was the idea? The idea was that we would cut up the sphere into very thin slices that were cylindrical. And since we were able to figure out the volume of a cylindrical disk, right? The idea was that we would bunch them all up together. We would cut up our sphere into very thin slices that were cylindrical in nature and add them all up. And the thinner those slices became, the closer the approximated value would get to the actual value um, of the volume. And so we were able to discuss that last time. So let me share my screen with you guys. Okay, so here we are. So just to, I guess, remind us a bit of what we're doing here, let's look at an example really quick. Um, so what if I want to find the volume, right, of the solid made by the revolution region by the following. Y is equal to 2 minus 1 half x. So hello, hello. Am I still here? Sorry about that, guys. My Zoom just like disappeared. I don't know what's wrong with it. I don't know if it's the rain. I don't know what it is. But we're back. Great. I'm back. Hope you guys are back too. Okay, so this is what I want to do, okay? I want to figure out what's the volume of the solid. Remember, we're dealing with three-dimensional figures now. And we create these figures by revolving a region that's originally two-dimensional, right? We revolve it around one of the axes for these cases, right? So what's the idea? Let's sketch this. Let's sketch the region first. Let's sketch the region. So this is where our drawing abilities come into play. So let me sketch this. And what do I have? I got y equals 2 minus a half x, right? So what is that? That's a line, right? Whose y-intercept is 2, right? So then I have my y-intercept being 2 here. Let me use pink for this. And then what else do I have? The slope, right? Negative 1/2. So what's the slope going to indicate for me? That I move down 1, right? I move down 1 over 2. So I'm going to be over here, my next point. And this is what I'm gonna get. I'm gonna get a straight line. And if only I can draw better straight lines. Something like this, right? And what else do I have? What else do I have? I got this line y equals 0. Y equals 0 represents what again? Represents the x-axis. Oops. The x-axis, right? So I got that region. And I also have these vertical lines here, right? These are vertical lines here. So I got x equals 1. I got these vertical lines. But of course, what do I want only? I want the region that's in between all of these lines. I want the region in between x equals 2, x equals 1, y is 2 minus 1 half x, and above y equals 0. So that region would be what? It's this region, right? So this is the region that I have. Now, what do I want to do with this region? I want to revolve it around the x-axis. Now, for those of you who have a very good spatial concept of what that would look like, what would happen if this two-dimensional and revolve it around? Yeah. So what did somebody say here? Would it look like a cup? Huh. What kind of cup is that? Now, I tried my best, I think last time, to give you guys a visualization of this. So I actually, it's kind of hard to do so from a two-dimensional point of view. But I'll see if I can give you guys a better understanding. And I'll show you through this little program that we have called Maple. And I don't know if you guys can see this. Hold on, it'll be something like this. So, can you guys see this? So do you see this strip here? Good. Do you see this line right here? This line right here? This is the that pink line that we had, 2 minus 2x, right? This is my my x-axis, and you start to see this is a three-dimensional rendering of it, right? So we got the y-axis. So we normally look at the x and the y-axis, correct? But then we have an additional axis called the z-axis, which gives us the three-dimensional aspect of it. But for now, let's look at the two-dimensional aspect. This is what we get. But we only want between 1 and 2, correct? So I'm going to change these bounds here from 1 to 2. So that a value, remember that a value represents the lower integral, the integration bound, and the b represents the upper integration bound. So I'm going from 1 to 2. And then it says here the line of revolution, right? The distance of rotation from the axis is when it's the horizontal axis, which is the x-axis, which equals 0. So if I display that, this is the piece that I get. Do you guys see this? And look at the region. Oh wait, let me put the region equal to 0 here and display. So guys, do you see this red? It became really red. Let me take away the volume here. This is my region, correct? Does everybody understand what I'm trying to do? Yeah, it is cool, right, Kirk? So of course I can't replicate this my own by myself. I wish I could. But this red region is that yellow striped region that we had. That thing is what we want to revolve around the x-axis. And when we do so, this is what we get. We get this little, it looks like, this is really called the frustrum of a cone. This is make believe like if this were to continue, right? It would create a cone and we have that base of it. We have like a base of a cone. And this is what we want to figure out the volume of. So what's the idea? The idea is that we create what? We create like discs. Do you see this? Do you see these discs? Let me make them less. So suppose we have 3 discs, right? All these discs here are what? They're cylindrical, aren't they? These are, yes, it's so much easier to see in 3D. Can you believe that? So cool, right? It's amazing what computers can do nowadays. So these are the discs that are useful to figure out the approximate volume. But then what's the idea, guys? We want to make these cylinders as thin as possible. So what happens when we augment the number of cylinders, right? Or the number of discs that appear? If you see here, right, it says the approximating sum. I don't even think they're giving us the right approximation. But the point is that as we increase the number of partitions, what would happen? It gets closer and closer, right? Of course, it gets closer and closer to the actual volume. So that's the whole idea. It's the same way. It's analogous to what we did in the beginning, right? We try to figure out what's the area underneath the curve. What do we figure out first? We figured out the area of what? We figured out the area of the rectangles beneath the curve, right? And then what's the idea? We make those rectangles as thin as possible, and we add all those up. And as we take the limit, as we make those that thickness as goes to 0, right? As thin as possible, infinitesimally thin, then we would get the actual exact area. In this case now, we're not taking slithers of rectangles, we're taking slithers of cylindrical discs. And those cylindrical discs have a volume. And we're making that thickness as thin as possible. We're making that n goes to infinity. But because of the cylindrical nature of it, the volume, right, has a certain formula there's a certain formula for the volume of a cylinder. So that's my little presentation for today. Hopefully you guys, I mean, I'm going to use this again for when we have more complicated, um, regions, as we will see. But now, hopefully you have a better understanding of what the region that we have two-dimensionally we start with, right? How that region becomes a 3-dimensional solid as it revolves around the x-axis. I know last time I didn't do a great. Yeah. So yeah, thank you, Professor Kramer. Professor Kramer is also joining us, guys, from the math department. So I think he enjoyed it as well. Yeah, I enjoy looking at these things on Maple because Maple is awesome. There's also Mathematica, which is another software package that exists. But anyways, sometimes a picture is worth 1,000 words, right? Okay, so now let's get back to it. Let's get back to the nitty gritty. So now that you guys have the visual understanding, I hope you guys now have a better clarity as to what is expected. So then now does it make sense that when I draw this region here, does it make more sense as to why I drew it the way I think I tried doing this last time? It looks something like this. Sorry, this should be a little thicker. Right? Is everyone in agreement? This is the way it would look. Yes, thank you, Professor Kramer. You all guys, uh, you can download this for free. So that's a perk that I guess not so many of us have mentioned out loud or announced, but you can download this from the CUNY email. It's a free software for you guys as students. So you guys can have your own little explorations as well. And there's so much more that you can do with this. Is not just the only thing that Maple does. It does a whole bunch of other assortment of things. So for those of you who, continue on with higher level mathematics, Maple would be an indispensable um, resource to help you go, guys, not just compute things, but also visualize things and so on. So yes, thank you, Professor Kramer, for that. Um, so then what's the idea, right? So always look at the big idea, look at the microscopic detail. So we have the big idea. We have the idea that we wanted this region that was originally two-dimensional to revolve around the x-axis. And in doing so, we create a three-dimensional solid. And now the task for us is to find the volume of that three-dimensional solid. But what's the idea for that? The idea is that we consider disks, right? We consider little disks, cylindrical disks. And the idea is that we take a whole bunch of them and we sum them up. So then what's the volume of a disk? What's the volume? Remember, it's cylindrical. Of cylindrical disk. So guys, remember this? What's the volume of a cylinder? Anybody? What's the volume of a cylinder? It's from like middle school.
Is it pi r squared times height?
That's right. That's right. Pi r squared times height. Now, in the context of this scenario, the height, right, if you look at it from the other perspective, the height, we're going to consider this as the change in x. This is going to be change in x, some thickness, right? Do I know the thickness? Not exactly, but I know some difference between the x values. And now the crucial part here is the radius. What's going to be the radius? Remember, we're using our x-axis as the axis for revolution. This is called the axis of revolution. This is the line for which we're making it the center, right, of our revolution. So our x-axis is the center, or I should say the axis of revolution. So we are revolving it around the x-axis. So my center is right here. So then that means that this is my radius, right? And how do we define our radius? What would be the rate? How do we express our radius in terms of x? Or what is the radius associated with in terms of, if I consider a particular x value here, right? Call it x sub I. What would be this length here associated with? It would be associated with what? Or it would correspond with what? Yes, Eliana, the radius. I'm asking for, what is the radius associated with respect to the x coordinate that this cylinder is sitting upon? So there's some x value, right? Who goes through this center right here. What would be this length here associated with? Right, David. It will be associated with the y value. Do you guys see that? This length here, right, known as the radius, is associated with the y value of my function. Do you guys understand that? And since we chose a particular x sub I, it's some disk. We don't know which one it is, but it's one of them, right? So this radius would be what? It'll be the function evaluated at x sub I. But we already know what that function is, right? This is our function here. So my radius is really 2 minus 1/2 x sub I. So then if I put that here all together, I would have that the volume of one disk is pi times what? 2 minus 1 half x squared. And I'm gonna put this x sub I here. Do you guys see how we're building this up? I'm starting with the volume of one disk. And then what's the idea? What's the idea? After I get the volume of one disk, what's the next thing that I'm going to do? Am I just going to use one disk? Or am I going to use multiple disks to find out? Right. I'm going to continue this whole idea and I'm going to find the volume of multiple disks, right? How many of them? So that's the question. So then I'm going to say, you know what? Let me approximate the volume. How do I approximate the volume of the solid? I'm going to take the summation of the what? The volume of several disks. So I'm going to take one of them, the ith one, and I'm going to go from 1 through n. I'm going to say, you know what? Let's make n of them. It could be 10, it could be 20, it could be 30, it could be 1,000, it could be 1,000,000 disks. And what's the idea? As n gets infinitely large, meaning that as the number of disks goes to infinity, which would signify that the thickness of those disks becomes thinner and thinner, the volume, the approximated volume, approaches the actual exact volume. So that's the idea. The idea is that as n goes to infinity, the thickness goes to 0, right? Remember what's thickness? Remember what the change in x represents? Recall this. Recall that the change in x was what again? It was b minus a over n, right? And what does n here represent? N represents the number of cylindrical disks. What does the change in x represent? It represents the thickness, quote unquote, right? Of disks. So as one gets bigger, the other one gets smaller, right? As you have more disks, the thickness of those disks gets smaller and smaller. So the idea is that as this goes to infinity, right, what happens? The approximated volume, so we have the following. As we take the limit and n goes to infinity of my summation here, what's the result, guys? As I take this limit. So again, this whole thing here is the approximate volume of solid by n disks. So if I have n of them, but I make that n go to infinity, what's the result? What's the result? Remember, this should remind you of what? This whole thing should remind you of way back when we started with Riemann sums. So if I take the limit of them, what happens? This becomes what? It becomes the famous and all-powerful what? No, David, not the area. Not the area. Because remember, remember, we're summing up volumes. We're not summing up areas. So we're adding up volumes of disks. The result, guys, is the integral. Remember, it's the integral from a to b of what? Of pi times 2 minus 1 half x squared dx. The whole question, the whole result is that this represents the exact volume of solid. Do you guys see the connection? It's all about what I'm trying to establish is the connection of what we've done in the beginning of the semester, right? In the beginning of the semester, this idea of integration was introduced because we were trying to figure out the area underneath the curve. Now we're taking that one step further. Now we're taking this concept of volume and we're extending it. But we're utilizing what we learned in the beginning. We're using Riemann sums, really, taking the limit of it as the n goes to infinity, and that becomes the integral. So then really what we care about is this. This is what we care about at the end of the day. But all of this, guys, all of this is just like the background. The background as to why is it that we're going to be using this formula or this kind of integral every time. So then what's my a and b again? Remember, my a and b are the left and are the lower and upper bounds of my integration. My lower bound of integration, right, is going to be 1 because my x values go from 1 to 2. So the volume of my solid, that's right, Kirk. The volume of my solid, let me change this. So the volume of my solid of revolution, right, is the integral from 1 to 2. And since pi is a constant, I can place that outside. And what's left? It's 2 minus 1 half x squared dx. Now, do you guys see that the setup is the most important part? Because I'm pretty sure from now, you guys are more comfortable now with integrating, right? So the integration aspect of it is more of the technical aspect, which is something that we've done a lot of. We've done integration with USUB, with trig, with all of these different techniques, correct? But now the important thing is not necessarily how we integrate, but it's why do we integrate? What's the big reason as to why we do it? And what's the result give us? The result represents a volume. So now at this step, I hope we find it a little bit more simpler to deal with, right? Because we're more comfortable with just looking at this now and integrating. So what's the first thing I do here, guys, when I want to integrate this? So how do I integrate 2 minus 1 half x parentheses squared? What should I do? I should square everything, right? So I should expand. So what happens? So I'm going to rewrite the integral. A lot of this stuff, right, guys, is rewriting the integral. So I'm going to rewrite integrand. And when I do so, what do I get? What happens when I do 2 minus 1 half x and I actually square it? I get what do I get, guys, when I square this? I expand it and I get what? You guys got to tell me. So when I FOIL, correct? When I no, guys, you have to FOIL. You have to FOIL. Oh wait, am I saying this right? Yeah, Ileana. Yeah, sorry, sorry, Ileana. That was not right. You have to FOIL, guys. So then when we FOIL, what happens? First term, right? You get the 4, and then you get double the inside curse. So you get 2x, right? And you get plus 1/4 x squared. So I think Kirk got that, and David got that as well. So good. So that's the most important step behind this whole process, rewriting the integral. integrand so that I could apply the anti-differentiation rules that we learned, right? So then, what's the antiderivative here? I get 4x, right? And then I get what? X squared over 2. And then I get what? I get 1/12 x to the third. And of course, I'm evaluating this at 2 and 1. So is everyone good so far? This is the antiderivative, right? We do the opposite of the power rule. And then, I don't know if you guys hear the rain behind me, but it's pretty bad out there. Isn't it only x squared? What do you mean, Kirk?
I don't know, isn't it divided by the power? So 2x divided by 2 would be just x squared.
Oh, that's right. Pardon me for that. Thank you, Kirk. Thank you. What did I write here? Oh, yeah, yeah. Okay, good. Thank you. That's right. It should only be x squared, not x squared over 2. Okay, and then what? And then we would plug in, right? 4 times 2 minus 2 squared plus 1/12 times 2 cubed. And all of this is being subtracted by 4 times 1 minus 1 squared plus 1/12 times 1, right? And then this becomes pi. This becomes what? Um, 8 minus 4 plus, this is what? 8 over 12 minus 3 plus a 12th. Now we love fractions, don't we? This becomes pi. This is 4 minus, this reduces to what? Divided by 2. And I get, divide this by 4, pardon me. And so we can reduce this, and I get 2/3 minus 3 minus a 12th, right? And this becomes pi. 4 minus 3 is 1, and then I can subtract minus 2/3. So actually, I should have just kept it as 8/12. I should have just left it as 8/12. Because then, uh, I'm just going to do this again. So this is negative 8/12. I rewrite it using the same denominator. I get pi. This is 1 minus 9/12. And this is the same thing as saying 3/4, right? So this is pi times 3/4. So the answer should be 3 pi over 4. Plus, oh, did I make a did I make another mistake? Yeah, just I think I made another mistake, right? Where is it? Four. Yeah, that was my mistake, guys. That's definitely appreciate that, Kirk. I made a little mistake. So this should be plus. Pardon me for that. This should be plus, not minus. I don't know where I got the minus from, to tell you the truth. So thank you for those who pointed it out for me. And appreciate that, Professor Kramer. Yes, I mean we all make mistakes. We really do. So then this, so then this becomes. But thank you for your graciousness. So this becomes should be plus 7/12 instead. So it's a quick fix. So this becomes 12 over 12 plus 7 over 12. So the answer should be 19 pi over 12. So are we all in agreement? Yes, no, maybe so. Yes, great. Thanks, Kirk. So then, just to make sure, right? Just to make sure there's no funny business, right? Let's say we were all wrong. Maybe we all made the same darn mistake. So let's see. So I'm gonna find a numerical value to this. So I got 19. Where is this? Where is pi? Pi, and divide that by 12. So I got 4 point, right? This is approximately 4.9741 right? And now let's see what Maple says. Do we trust Maple? I think we all trust Maple now, right? Well, at least you trust it more than my drawing ability. And look what Maple says. The volume of the solid. It's you see how it set it up? It is set it up exactly the way we set it up. Do you guys see? Maple is very, very good. You just met Kirk. It's okay. I'll tell you she's pretty good. And you see the volume here? Exactly what we got. Of course, they give you the approximated decimal version of it. They don't give you the beautiful exact expression that we got, 19 pi over 12. But we get the same thing. So good. So Maple says we're good. You all say we're good. So we're good. So, but again, the idea is what I want to stress. And so I want to see if you guys understand the big idea. So what is the big idea? The big idea is this idea that I can figure out the volume, right? I can figure out the volume of a solid revolved around an axis by finding what? So the volume of a solid revolved around, sorry, the volume of a solid, right? When you revolve it around the x-axis is given by the formula pi from a to b of r of the, let me call this the radius squared dx, where the radius is the function between a and b. So in reality, we would actually write it this way. So this is really the big idea that I want you guys to leave with. Now, this is known as the disk method, right? They call it the disk method. And why do we call it the disk method? Is because of everything we've discussed previously. This here comes from what? It comes from the taking the approximation of a number of cylindrical disks and making those disks as thin as possible, meaning that we get this limit and make n go to infinity, which results into this beautiful, very compact, elegant expression. It's the integral. So that's why we call it the disk method. And where does f of x come from? What does that represent? That represents the radius of these disks. Do you guys see that? So I know it may take some time, but try to make that connection. Don't just use this formula. Yeah, this is called the disk method. We'll talk about the washer method right after this. So this is called a disk method because these are solid disks that we're adding up. The washer method, which we'll discuss, is when we have like a ring of disks, the disks that have a hollowness in them, that have a circular hollowness. That's going to be next. But the idea is that we're taking up disks that are cylindrical, solid, which we can find the volume for each of these disks, but we're making that approximation, right? That original approximation, we're making that exact by making them as thin as possible and including an infinite number, quote unquote, of disks, which results in the integral, which results in the exact volume of the solid. And that's what I'm trying to express. Okay? Any questions about this? Is this clearer now than the little introduction that I made last time? Is it better now? Do we have the visualization of it now? I know my drawings are terrible. It's better. Great. This is progress. It's what I like to hear. It's better than before. All right. Okay, great. Great. Um, so why don't we let's look at let's look at more of these examples here. Okay. So okay, maybe you guys are, you know what? I'm comfortable with this. I kind of get this. Kind of get it. Now, what if I want to do the following? Find the volume of solid created by revolving region bounded by the following functions around the y-axis. So now the question is, you know how we've revolved it around the x-axis? What makes the x-axis so much more special than the y-axis? Can't I also do the same exact kind of idea around the y-axis? So then what would be the difference here? So then let me give you the functions here. So one of them will be x equals 2 rad y. Pardon me. The other one will be x equals 0, and I got y equals 0. So then y equals 9, pardon me. So then let's sketch this. So really sketching is probably one of the most important things here because it gives us an idea of how to proceed. So let's look at this. Let's look at these first. X equals 0. What does x equals 0 represent? X equals 0 represents what? A vertical line, right? And that represents the y-axis. That's right, Eliana. It's the y-axis. So this is x equals 0 here. So this is one of the lines that I'm going to extend here with the dotted line. And y equals 9 is a horizontal line, correct? So I'm going to draw a horizontal line here. So I got y equals 9. And now, what do we have here in number 1? X equals 2 rad y. What in the world is that? We're more comfortable with saying y is a function of x. But you have to also be twice as the same as comfortable as finding functions in terms of y. So does anybody know what this function here looks like when you graph it? Remember how we discussed these kind of problems? What kind of function is this? When we have this square root, it's called it is going to be a parabolic in nature, yes. But this is a square root function, guys. This is a square root function. Now, do you guys remember how we would approach these kind of problems? How do we approach it? Oh, okay. So you David, you solved for y, right? Is that what you did? Yeah. So that's one way to consider it, which is fine. So let's see that. So what happens if I were to do that, right? If I say x equals 2 rad y, right? And let's say if I solve for y, What would I get? I'll get x squared equals 4y, right? Because I squared both sides. And then I'll get what? I'll get y is equal to 1/4 x squared. So I guess you guys are more comfortable with this, and I understand. So this is a parabola, correct? That looks something like this. Now, I would include the other half as well, correct? I would include the other half as well if I were to graph this. But remember, this comes from this original equation. So actually, in this original equation, we're only looking at the positive, this is called the principal square root. So we're only going to get positive values here for x. So do you guys see that? Do you guys see that this portion here, this graph here represents the whole parabola here? But the original equation is only talking about the positive side. So I only care about this portion here. I do not care about the other portion. Do you guys see that? So you just have to be careful with this, guys. You have to be careful. Or you can make x equals 9, x equals 9y, since everything else is x equals y. Well, not everything else is not x equal to y. So I don't know if if what you're saying, Ileana, is that remember what we said. We're so comfortable with the other way around, right? We're so comfortable with y being a function of x. So then what I would say is why don't we switch the x into y's and call it y equals 2 rad x? Don't we know what this looks like? This will look like a square root function, correct? But now we have to kind of like put our head and look at it from the perspective where the x-axis is my new vertical axis and my y-axis is my new horizontal axis. And if I were to look at it that way, this graph will be exactly the graph that I just drew here. Do you guys see that? That's one way I look at it. I don't know if that confuses things or clarifies things for you. But that's the way I would look at it. I would look at it as this being a function of x, and then rotating my head and then visualizing this as the graph. But the idea is that I only want this piece. And what's the region that's bounded between this graph here, this line here, and this line here? Well, you have this line, you have this line, you have this graph here. And that region that's bounded is this. So we have this. That's the region that I'm going to revolve. And when I do revolve, what happens? I'm revolving it around the y-axis. So then what's still going to be the results of this region being revolved around the y-axis? It's half a sphere. It's not necessarily spherical, but we would get something like this, right? Wouldn't we? Something like this. Looks like a pot of some sort, right? Or a dome. That's a good one, Kurt. Yeah. It's like a dome. Exactly. And now what's the difference here? What's the difference here? My cylindrical discs will not be what? It will not be vertically made. You see how these discs are when you slice your when you slice your volume vertically, we create these discs. Now instead of slicing it vertically, how are we going to slice it here? We're going to slice it horizontally. Do you guys see that? Do you guys see how this idea, the big idea hasn't changed? We're still slicing things up. Like these are also known as, like, we're still considering the cross sections, aren't we? When we slice something in this way, in this manner. Now the only difference is now it's horizontal, and we're stacking these up. We're stacking all of these discs. We're stacking them up vertically, whereas in the other example, we're slicing them horizontally, and joining them horizontally. So now the question is, what is this volume then? What is the volume of this? Uh, what is the volume of this cylindrical disc? Well, it has a thickness, doesn't it? What's that thickness? Well, of course, this is pi r squared times the height. But what is that thickness? What is that height? What are we going to call it? Remember in the other example, we called that thickness or that height of the cylindrical disc the change in x? What are we going to call it here? Yes, that's right, Ileana. That's right. It's the change in y. This is a change in y, guys. So you're like, okay. And then what's going to be the radius? This is the hardest part. If you get this, then everything is smooth sailing from here. It's going to be what? The radius, right? The radius is going to be this little strip here. This is my radius. But now, instead of it being as a function of x, it's going to be a function of y. So then what we care about is the radius here. The radius. This is going to be the x values as a function of, so I'm going to call this change in x sub I. It's going to be with respect to the y coordinates. In the other example, right, it was the y value associated with the x coordinate. In this case, it's switched because our axis of revolution is no longer the x-axis, it's the y-axis. So it's the same thing, just switched. That's all it is. Do you guys understand that? And don't we know what that is? We have it. We already have our function in terms of y. We already have our x coordinate as a function of y. So really what we have here is this. Is 2 rad y squared. That's the volume of one disk. But then what are we going to do? We're not going to just get one disk. We're going to get a multiple of disks, aren't we? If we stack them up, what would we get? We would get the approximated volume. So what would be the approximate volume? It's if we take the sum, right? As I goes from 1 through n, as we take an n, an arbitrary number of these horizontal disks, right? So this would be pi times 2 square root of yi squared change in y. But then what do we do when we take all these disks and we make those thicknesses as thin as possible? In other words, what if we include an infinite number of these disks with infinitesimally thin thicknesses? What does it become? What does it become? As n goes to infinity, what do I get? The approximate volume becomes what? It becomes the integral, guys. And I'm going to use different the letters for the integration bounds. From c to d of what? Of pi times 2 rad y squared dy. Now, what are going to be my integration bounds of? Remember, in the other example, the integration bounds were the interval of my x values. But in this case, because I revolve it around the y-axis, my integration bounds will not be it's not going to be the interval of the x values. It's going to be the interval of the y values instead. So then my highest y value is what? In this example here, it's 9. And my lowest y value would be what? 0. That's right, Kirk. So then the result will be what? Pi from 0 to 9. And then I can square this stuff, right? Now I can write this as what? 4y dy. And then integrating this, I can take out that 4 out, right? I get 4 pi from 0 to 9y dy. This becomes 4 pi. What's the antiderivative of y? Y squared over 2. And I'm evaluating this from 0 to 9. And now I'm plugging it in. I'm plugging in the 9, and I get 9 squared over 2 minus 0 squared over 2, right? The zeros here, it just becomes 0. And I get 81 over 2 multiplied by 4 pi. The 2 goes into 4 twice, and I get what? 162 pi. And so then the volume of this solid that I created by revolving that region around the y-axis, that volume is 162 pi square units, cubic units. Does this make sense? Or did I lose you all? Do you guys see how this is connected with the other example? It's just that now this example here, we're revolving it around the y-axis instead of the x-axis. Do you see how it's just switched? Instead of the bounds of integration being the x values, right? It's the y values instead. Instead of the integrand being a function of x, it's a function of y squared. That's all it is. And then after that, it's just, after that, if you can make that connection, then integrating these things right now, they become second nature, or it should be. It's becoming clearer and clearer. Very good. If you guys have any questions, if this doesn't make any sense, if anything, just tell me. It's okay. I know it could be kind of confusing, especially when you're not used to seeing a certain thing, right? You're not used to maybe seeing x being expressed as a function of y and understanding what that sketch is like. Once you're able to do that, then everything should be clear. Yes, it is the tricky part is making everything fit nicely. But when it does, right, it's very nice. It's very nicely put. Okay. So I guess I want to say what's the takeaway from all of this, right? So if I take a region, and revolve it around x-axis. So I'm gonna give you just like a generic function, right? So if I have a function like this, so if I say this is y f of x, right? This is y and this is x. And I want to take the piece from A to B, and I want to take this region here. If I want to figure out what is the volume of this random region, right? What is the volume of that solid that's created after I revolve it around the x-axis? What would be the volume? The volume would be pi integral from A to B, right? And then it would be the function of x squared dx, right? Because you could think of this as finding the, some people would say the cross-sectional area, right? They would say that this is really the you're integrating the cross-sectional area. So some textbooks call it, they write it this way, right, as A to B of A of x dx, where A of x is known as the cross-sectional area of solid. So if you're able to determine, and if that cross-sectional area is some very simple shape throughout the whole, if you can slice if every cross section is easily found to be some kind of maybe circle or something, elementary region, then you can always do this. But in this case, we're considering cylindrical discs, right? These are going to be cylindrical discs that will be found when we cut up um, our solids. And if we take another region, right? And we take a region what did I say? And revolve it around the y-axis instead. So now I'm going to write something similar, but now I have some kind of function that looks like this. And this is, I'm going to call it C. This I'm going to call it D, right? And I'm revolving it around the y-axis. So this is the region that I'm considering. And this graph is going to be a function of y. And if I revolve it around, right? If I revolve it around, then this solid here will be found, the volume of the solid will be found by pi from c to d of f of y squared dy. Okay? And then again, it's the same idea, right? We have some kind of cross-sectional region area here. This is a cross-sectional area, but this will be as a function of y instead. And again, these cross-sectional areas here are going to be circles. That's why we have this pi r squared business here going on. So when we have the region that's revolved around the x-axis, we take the function, square it, integrate it from a to b, and have that pi in front, which is representing the circular cross-section that we get when we slice it vertically. And if we were to revolve it around the y-axis instead, then the region that we would get cross-sectionally will also be circles, but in this case, the radius will be determined by the function in terms of y. And my x values are going to be the bounds of integration for this example, and my y values, my upper and lower y values will be the integration bounds for these kind of examples. Does that make sense? This is known as the disk method. Okay. So let's see. I have a few minutes left. So now if this started making more sense, we're gonna build upon this, and we're gonna discuss something that's called the washer method, quote unquote washer method. So we discussed about the disk method approach of finding the volume of a solid, but now we're gonna have something that's called the washer method. And this occurs when we don't have a complete solid figure. When we have some kind of figure that's created from two functions, right? But there's like a hollowness within it. And we discussed that last time a bit. But let's look at an example first. So what if I want to find the volume of solid formed by rotating, let's say revolving a region bounded by the following functions. About the x-axis. Okay, so then what are these functions? Well, the first function I'm going to say is y equals 1/4 x squared. The second function will be y equals 5 minus x squared. So I'm going to take both of these functions and I'm going to revolve it around the x-axis. So what is that going to look like instead? So let's sketch a graph. And then we have to graph it like, yeah, I think this is fine. So then, let me see this. So then I'm going to graph the parabola that's facing upward, right? Hold on. So I should make this a little bit thinner. Like a little wider. Yeah. So here I have y equals 1/4 x squared, right? And then I'm going to have the other curve, parabola that's facing downward. It looks something like this. If it was only symmetric, it would be better. But this would be the y-intercept. And what is that I want to do now? I want to take this region and I'm going to revolve it around the x-axis. Now the question is, what happens when I have two curves now? What happens if I have two curves? And then that region that's bounded between those two curves, I want to revolve that around the x-axis. What is that going to look like? So that's gonna challenge our perception a bit more, right? How it would look like. Twice the fun. Well, I'm glad you feel that way. So let me give you guys a better visualization of it by Maple. So the top function, right, f of x is going to be a top function. The top function would be 5 minus x squared. And then the lower function would be, I'll write it as 0.25 times x squared, right? And for now, I'll just make this 0 to, let's see, 3, negative 3. So if I do this, let's see what happens. Oh, sorry, it's just horizontal. So let me take out the discs. Do you guys see this? Let me take out the volume for now, and let me guys just make you see. You see how this is what we drew, right? This is the green one represents the pink that we have, right? And this dark blue represents the light blue that we drew, that I drew. So you see f of x, right? I don't know why it's always like on an angle. But this one here represents the parabola that's pointing downward. This one here represents the parabola pointing upward, right? And what is it that I'm trying to figure out? I'm trying to figure out is what happens when I take this region. And the region that I'm interested in is not that well, I'm not, in this case, actually, it's from 2 to 2, pardon me. This is from negative 2 to 2. Negative 2 to 2. So I'm interested in this region that we sketched, right? And I want to revolve that around. And I'll show you why we get the negative 2 and 2 later, because we set it equal to each other to find the points of intersection. And then when I revolve it around the x-axis, this is what I get. Do you guys see that? I don't know if this is helpful. And you see how this is like, Inside here, I don't know if I can make this bigger. Can I make this bigger? No, I can't. Inside here, it's hollow. There is no volume. There's just space inside. Do you guys see that? And now the idea is, what happens if I want to apply disks? Like how do I approximate this volume? Do you see how my disks now are no longer solid disks? Now there's holes inside. There's like a thick there's a hole inside here. Now the question is, why does that happen? If I increase the number of disks, all of these disks now are hollow within, and that's because of these two graphs that I have. Do you guys see that? So the idea is that the result, right? The result of revolving this region around is I get something like this. I get some kind of like, I get something like this. Right? Something like this. This is not the greatest, okay? Yeah, I can't really draw this whole thing here. But do you see something like this? It's something like this. Well, I'm so glad we have Maple, because imagine trying to understand just by looking at my visual. It would be impossible. But this is the idea, guys. And the idea is that we're not gonna have enough time to go over it exactly right now. But I'll give you the idea. The idea is that I have a cylindrical shell, right? A cylindrical disc, but then I also have to take care of this piece here. And so then this becomes what's called an annular ring. It becomes a ring of a disc, not a solid disc. It becomes a ring of it. And so the idea is that I'm going to find the volume of the bigger portion, right, of the whole thing, and I'm going to subtract off the volume of that smaller disc inside. So if I have the big disc, which is this whole big thing here, and I hollow out the inside here, then I'll get the volume of the annular ring. And then if I approximate the volume by summing up all these annular discs, and I make those annular discs, annular rings, as thin as possible, find a limit as make n go to infinity, then I'll get the integral. And then we have what's called the washer method, because people call these annular rings, they call them washers as well. So we'll finish that up next class. So that'll be all for right now. But was this better? Do you guys could you guys understand this better now? Yes, yes, yes. I see a lot of yeses, and I'm glad. I'm glad that now this is better understood. And this is what I enjoy doing. I enjoy this portion of Calc 2, because I feel like, okay, very good, Moses. Very good, going along with the textbook. So this is what I enjoy, because hopefully, maybe with some more thought and consideration, you start to see how everything that we started from the beginning of the semester, how it ties back in. Now we're going from area and we're moving up to volume. And that's where it gets interesting. And it's very interesting how very simple concepts that you've discussed before, right, in geometry, now it's so interesting, right? It's so interesting how volume and area, well, now volume, um, which you may have just considered that, oh, it's just the volume of a sphere is just this formula. The volume of a cylinder is just this formula. Now those formulas that are elementary, right? Now they're useful to figure out volumes of more complicated regions, of more complicated figures. But everything has a progression, right? We start from something very basic, and then we build upon it, and it's beautiful to see, especially if you have things like maple, which makes things beautiful and easy to visualize rather than my drawings. All right, guys. So that'll be all for today. Any questions, let me know. If not, I'll see you all Wednesday. All right.